Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Let your body settle into whatever surface is holding you. There's no rush, no urgency, just this quiet moment and the story we're about to share. Where in the world are you watching from? A darkened bedroom where the day has finally released its hold? A quiet corner where the noise of the world feels far away? Wherever you are, you're welcome here. Tonight we're going to explore something that sounds almost impossible to believe. We're going to journey to the edge of the observable universe, to places so distant that the light reaching our telescopes left those regions when the universe itself was young. We'll discover what scientists have found in these impossibly remote corners of space, understand why some of these discoveries challenge everything we thought we knew, and contemplate what it means to look so far that we're essentially seeing backward through time itself. It's a journey that spans nearly 14 billion years, across distances so vast they make our minds struggle to comprehend them. But don't worry. This isn't going to be a frantic rush through alarming revelations or disturbing cosmic horrors. Instead, we'll move slowly and carefully through the science, the observations, and the quiet mysteries that emerge when we peer into the deepest darkness. We'll explore what these distant galaxies tell us, what patterns scientists have noticed that don't quite fit our expectations, and how these discoveries are gently reshaping our understanding of everything. Of the cosmos, a like and subscribe really of the cosmos, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting these journeys into the unknown. So settle in. Let your shoulders drop away from your ears. Take a slow breath. And let it out even slower. And let's begin our slow drift toward the edge of everything. There's nowhere you need to be right now. Nothing you need to do. Just listen. And let the story unfold. The universe is patient. We can be too. Let's begin with something beautiful and simple. When you look up at the night sky, you're not seeing the universe as it is right now. You're seeing it as it was. Light takes time to travel, and even though it moves faster than anything else we know, the universe is so vast that light from distant objects takes years, centuries, even millions or billions of years to reach us. The nearest star beyond our sun, Proxima Centauri, is a little over 4 light years away. That means when you see its faint gleam in the sky, you're seeing light that left that star 4 years ago. You're looking 4 years into the past. It's a gentle kind of time travel, one we experience every time we look up. Now extend that principle outward. The Andromeda Galaxy, our nearest large galactic neighbour, lies 2.5 million light years away. When you photograph Andromeda, you're capturing photons that began their journey when our earliest human ancestors were just beginning to walk upright on the African savanna. The light is ancient, carrying information from a universe that existed long before we did. But what happens when we look even farther? What happens when we build telescopes powerful enough to gather the faintest whispers of light from the most distant reaches of space? This is where our story truly begins, and it starts with a profound realization that emerged from decades of astronomical observation. The farther we look into space, the farther back in time we see. This isn't metaphor or poetry. It's literal. A galaxy 10 billion light years away appears to us as it was 10 billion years ago, when the universe itself was less than 4 billion years old. We're not just mapping space when we build our cosmic atlases. We're mapping time. We're creating a visual history of the universe's development, watching it grow and change and evolve across the eons. And this brings us to something equally remarkable. There's a limit to how far we can see. Not because our telescopes aren't powerful enough, though, that's certainly a challenge, but because there's a fundamental boundary built into the structure of the universe itself. The universe is approximately 13.8 billion years old. That means the most distant light that could possibly reach us would have been travelling for 13.8 billion years, emitted from regions of space when the universe was brand new. This boundary, this cosmic horizon, is called the edge of the observable universe. It's not an edge in the sense of a wall or a cliff. Space likely extends far beyond what we can see, perhaps infinitely. But there's only so much universe we can observe, limited by the age of the cosmos and the speed of light. Beyond that horizon lies a region of space whose light simply hasn't had time to reach us yet. It might never reach us, in fact, because the universe is expanding, and in some distant regions, space is expanding faster than light can travel through it. For most of human history, we had no idea this edge even existed. We looked up at the stars and assumed they went on forever, unchanging and eternal. But in the 20th century, astronomers discovered that the universe has a history. It had a beginning. It's been growing and cooling and changing for nearly 14 billion years. And that means when we look to the farthest distances, we're seeing the universe in its infancy, in its earliest moments of existence. What we find there, at the edge of observation, is both beautiful and profoundly strange. And it's this strangeness that has captured the attention of scientists around the world, because what we're seeing doesn't quite match what we expected to find. The universe's earliest moments, it turns out, hold secrets we're only beginning to understand. Let's turn our attention now to the tools that allow us to see these impossible distances, to gather ancient light and decode the messages it carries across billions of years of cosmic history. The human eye is a remarkable instrument, but it has limits. On a clear, dark night far from city lights, you can see perhaps a few thousand stars with your naked eye. You can make out the cloudy band of the Milky Way, our home galaxy, stretching across the sky. If you know where to look and conditions are perfect, you might even glimpse the Andromeda Galaxy as a faint smudge of light. But to see the edge of the universe, to gather light that has travelled for more than 13 billion years, you need something far more powerful than human vision. You need instruments capable of collecting photons so ancient and faint that millions of them arrive every second and yet barely register. You need telescopes that can see not just across space, but across time itself. The story of seeing deeper into space is also the story of building better light buckets. That's essentially what a telescope is, a device for collecting light. From handheld refractors to massive reflecting telescopes perched atop mountains where the air is thin and steady. In the 20th century, this quest for light-gathering power accelerated dramatically. Telescopes like the 200-inch Hale telescope on Mount Palomar in California, completed in 1948, opened new windows into deep space. The Hubble Space Telescope, launched in 1990, removed the blurring effects of Earth's atmosphere entirely, peering into the cosmos with unprecedented clarity. But even Hubble, magnificent as it is, couldn't see all the way to the edge. The most distant, earliest galaxies emit their light primarily in infrared wavelengths, stretched by the expansion of the universe itself into redder and redder colours. To see these most ancient objects, you need a telescope specifically designed to detect infrared light. You need an instrument so sensitive it can pick up the heat signature of a bumblebee on the moon. You need something like the James Webb Space Telescope. Launched on Christmas Day in 2021, the James Webb Space Telescope represents the pinnacle of our light-gathering ambitions. Its primary mirror measures 21 feet across, composed of 18 hexagonal segments, made of beryllium and coated in a microscopically thin layer of gold. Gold reflects infrared light better than any other practical material, and every surface of Webb is optimized for this specific task, gathering the faint infrared whispers from the universe's earliest epochs. Webb doesn't orbit Earth like Hubble does. Instead, it sits at a gravitational balance point called L2, about 1 million miles from Earth in the direction away from the Sun. There, shielded from the Sun's heat by a tennis court-sized sunshield, Webb's instruments are kept at temperatures just barely above absolute zero. This extreme cold is necessary because infrared light is essentially heat radiation, and the telescope itself must be colder than the things it's trying to observe. Otherwise it would blind itself with its own warmth, like trying to see stars while pointing a flashlight at your eyes. When Webb opened its golden eye and began surveying the deep universe, astronomers expected to see ancient galaxies. They expected to look back to within a few 100 million years of the Big Bang and observe the first generation of stars forming in small, primitive galaxies. They expected these early galaxies to be faint, small, and chaotic, the cosmic equivalent of rough drafts before the polished final version of galaxies like our own Milky Way. What they found instead was something unexpected. The early universe, it turned out, was far more sophisticated than anyone had predicted. The galaxies Webb discovered in those distant reaches weren't all small and primitive. Some were large, structured, and bright. Some contained far more stars than they should have been able to form in the time available. Some showed signs of having already undergone multiple generations of star formation and evolution. It was as if we'd expected to find rough stone tools in our archaeological dig, and instead uncovered precision-crafted instruments. The universe, in its youth, appeared to have been far more advanced in its development than our theories suggested was possible. This wasn't necessarily wrong or disturbing in a frightening sense, but it was unsettling to our understanding, a sign that something in our cosmic timeline needed adjustment. These observations didn't come from Webb alone, of course. Ground-based telescopes like the Atacama Large Millimeter Array in Chile, the Keck telescopes in Hawaii, and others contributed pieces to this puzzle. But Webb, with its infrared vision and exquisite sensitivity, provided the clearest views yet of these impossibly distant realms. And the more astronomers looked, the more they realised that the edge of the universe held surprises we're still working to understand. Let's consider what these observations actually revealed, and why they've prompted such intense scientific discussion, and in some cases genuine puzzlement about what we thought we knew. Picture the early universe. In the moments after the Big Bang, there were no stars, no galaxies, no planets. There was only energy, gradually cooling and condensing into the simplest elements: hydrogen, helium, traces of lithium. The universe was hot, dense, and nearly uniform, with only the tiniest variations in density from one region to another. As the universe expanded and cooled, those tiny variations mattered. Regions that were even slightly denser than average began to pull in more matter through gravity. Over millions and then hundreds of millions of years, these denser regions collapsed into the first stars. Those stars lived, died, created heavier elements in their cores, and seeded the cosmos with the raw materials for planets and life. Eventually, countless stars gathered together into gravitationally bound systems we call galaxies. This process takes time. According to our understanding of cosmic evolution, the earliest small galaxies should have formed perhaps 100 to 200 million years after the Big Bang. These would have been modest things, containing maybe millions of stars rather than the hundreds of billions we see in large modern galaxies. Over time, these small galaxies would merge and grow, slowly building up into the grand spiral and elliptical galaxies that populate the universe today. The timeline seemed clear, the physics seemed sound. Computer simulations of the universe's evolution, running on the most powerful supercomputers available, consistently predicted this gradual bottom-up assembly of structure. Small things first, then larger things, then larger still, across billions of years of cosmic history. Then Webb started sending back data from the universe's first billion years, and that clear timeline began to blur. Astronomers found galaxies that appeared too massive, too bright, too well developed for their age. It was as if someone had fast-forwarded the cosmic clock, compressing what should have taken billions of years into just hundreds of millions. One particularly striking example came from observations made just a few months after Webb began science operations. Astronomers identified several galaxy candidates that appeared to exist when the universe was only a few 100 million years old. Nothing unusual there. That's exactly when we expected to find early galaxies. But these weren't the small primitive system predicted by theory. Some appeared to contain billions of stars. Some were already showing signs of mature stellar populations, with older red stars mixed among younger blue ones. The problem is straightforward if you understand stellar evolution. Stars form from collapsing clouds of gas. The most massive stars burn bright and die quickly, living only a few million years. Smaller stars like our Sun live much longer, billions of years. The mix of star types we see in a galaxy tells us something about that galaxy's history. If you see old red stars, the galaxy must have been forming stars for quite a while already, long enough for earlier generations of stars to age and cool. But in these early Webb observations, we were seeing signs of aged stellar populations in galaxies that existed when the universe itself was barely old enough to have formed stars at all. It's like finding a 50-year-old tree in a forest you know was planted last year. The math simply doesn't work unless something about our understanding needs revision. Now. Let's be clear about what this means and what it doesn't mean. This doesn't mean the Big Bang Theory is wrong, or that the universe isn't 13.8 billion years old. The evidence for those conclusions comes from multiple independent sources and remains rock solid. What it might mean is that our understanding of how galaxies form and grow in those earliest epochs needs refinement. Perhaps star formation happened more efficiently than we thought. Perhaps galaxies assembled faster than our models predicted. Perhaps there are physical processes we haven't fully accounted for. Science is comfortable with this kind of uncertainty. In fact, this is exactly how progress happens. We make observations that challenge our expectations, and then we work to understand why our expectations were wrong. We refine our models, test new hypotheses, make additional observations. Ordinary galaxy in an incomprehensibly ordinary galaxy in an incomprehensibly vast universe. But there's something undeniably profound about finding your timeline challenged at such fundamental levels. These aren't small adjustments to minor details. These are significant questions about how the first structures in the universe came to be. And as we'll see, the unexpected galaxies are only the beginning of what Webb and other telescopes have revealed at the edge of observation. Other observations added to the puzzle. Some distant galaxies showed unusually high concentrations of heavy elements, elements that should only exist after multiple generations of stars have lived and died. Yet here they were, present in galaxies that should have been experiencing their first burst of star formation. It was chemical enrichment happening on an impossibly fast schedule, another piece of the cosmic development puzzle that didn't quite fit the expected pattern. These findings sparked intense debate in the astronomical community. Papers were published, analysed, critiqued, and defended. Some scientists proposed modifications to galaxy formation theory. Others suggested that the distance measurements might be slightly off, making these galaxies younger than they appeared. Still others wondered if there might be exotic physics at play in the early universe, processes that don't occur in the modern cosmos. As I share this with you now, the debate continues. New observations refine our understanding month by month. Some of the earliest "zero" galaxy candidates have been reanalysed and found to be somewhat less massive than first thought, though still surprisingly large. Others have held up to scrutiny and remain puzzling. The scientific process unfolds slowly, carefully as it should, and through it all, we're gaining an increasingly detailed picture of what the universe looked like in its youth, even if that picture includes elements we don't yet fully understand. Which brings us naturally to consider another unexpected finding at cosmic dawn, the presence of structure and order where we expected chaos and simplicity. If you could zoom out from Earth and see the universe at the larger scales, you'd notice something remarkable. Galaxies aren't scattered randomly through space. They're organised into structures. They cluster together in groups and superclusters, connected by long filaments of galaxies and dark matter. Between these filaments lie vast voids, regions of space with very few galaxies. This organisation is called the cosmic web, and it's one of the most beautiful structures in nature. Picture a three-dimensional spider's web made not of silk but of galaxies, spanning billions of light years. The strands of this web mark the places where matter has collected under gravity's influence. The voids represent regions where matter has been pulled away, drawn toward the denser filaments and nodes. We've known about the cosmic web for decades. Large-scale surveys of the nearby universe have mapped it in exquisite detail, showing exactly how galaxies trace out this grand architecture. But we've always understood the cosmic web as something that developed over time. In the early universe, matter was much more evenly distributed. Only gradually, over billions of years, did gravity sculpt the smoothness into the web-like structure we see today. Or so we thought. One of the surprises from observations of the distant universe is that this cosmic web appears to have assembled much earlier than expected. Using Webb and other powerful telescopes, astronomers have traced the web's filaments back to epochs when the universe was less than 1 billion years old. They found that even in these early times, galaxies weren't just scattered randomly. They were already showing signs of clustering, already beginning to trace out the patterns that would eventually become the grand cosmic web we see nearby. This might not sound particularly disturbing at first. So galaxies clustered together early. So what? But remember, structure formation takes time. For galaxies to cluster, matter has to flow through space under gravity's influence. That flow happens at finite speeds, limited ultimately by the speed of light. The denser a region becomes, the stronger its gravity, and the faster it can pull in more material. But this is still a process that unfolds over cosmic timescales. Finding well-developed structure so early in cosmic history suggests that either the process started earlier than we realized, or it proceeded faster than our models predict, or both. It's another piece of evidence that the early universe was more dynamic, more active, more quickly evolving than the simpler picture we'd built up from theory and nearby observations. There's a particular observation that captures this beautifully. Astronomers using Webb identified a protocluster of galaxies, a region where dozens of galaxies were already gathering together, forming what would eventually become a massive galaxy cluster. This protocluster existed when the universe was only about 650 million years old, less than 5% of its current age. In the modern universe, galaxy clusters are enormous structures, the largest gravitationally bound objects we know. They contain hundreds or thousands of galaxies, vast clouds of hot gas, and tremendous amounts of dark matter. The process of building a cluster should take billions of years as smaller groups merge and accumulate. Yet here was a protocluster, already well on its way to formation, incredibly early in cosmic history. What this tells us is that the seeds of structure, those tiny density variations present in the very early universe, must have been more pronounced than we thought, or they must have led to structure formation more efficiently than our models predicted. Either way, it's a revision to our understanding of how the universe organized itself from initial near uniformity to the rich tapestry of structure we see today. And there's something profound about this, something that goes beyond just adjusting parameters in computer models. The cosmic web is the stage upon which all cosmic drama unfolds. It determines where galaxies form, where stars ignite, where planets coalesce, where life might emerge. If this structure assembled differently than we thought, it means the entire history of cosmic evolution needs reconsideration in some ways. Let's think about what this means for understanding our own origins. The Milky Way didn't form in isolation. It formed as part of the cosmic web, in a particular location with a particular history of matter inflow and galaxy interactions. Our solar system, our Earth, we ourselves are products of this grand cosmic architecture. The atoms in your body were forged in stars that formed in galaxies that clustered together according to patterns set down in the early universe. If those patterns assembled faster and earlier than we realized, it suggests the universe was more prepared for complexity, more ready for the emergence of structure than we previously believed. It's not disturbing in a frightening sense, but it is humbling. It reminds us how much we still have to learn about the cosmos, how tentative our understanding remains despite all our sophisticated instruments and elegant theories. But perhaps the most intriguing aspect of the early cosmic web is what it might tell us about dark matter, that mysterious substance that makes up most of the matter in the universe, but has never been directly detected. The cosmic web is primarily a web of dark matter, with galaxies simply marking the densest nodes where normal matter is collected. If the web assembled early, it means dark matter was clumping together early, pulling normal matter along with it. Some scientists have suggested that observations of the early cosmic web might provide clues to dark matter's nature, might help us distinguish between different theoretical models of what this mysterious substance actually is. It's a long shot, but the early universe has a way of revealing fundamental physics more clearly than the complex modern cosmos. When things are simpler, hotter, denser, the basic rules stand out more sharply. This leads us into territory that becomes increasingly abstract and theoretical, but no less fascinating for that. Because another surprise waiting at the edge of the universe involves something even more fundamental than galaxies or structure. It involves the very fabric of space itself and how it's evolved over cosmic time. The universe is expanding. This isn't controversial or speculative. It's one of the best established facts in all of science. When astronomers look at distant galaxies, they see that light from those galaxies has been stretched to longer, redder wavelengths. The farther away the galaxy, the greater this redshift. This pattern can only be explained if space itself is expanding, carrying galaxies apart from each other like raisins in a rising loaf of bread. Edwin Hubble first noticed this pattern in the late 1920s, though he didn't fully understand its implications. Over the decades since, astronomers have refined their measurements, mapping out exactly how fast different parts of the universe are receding from us. What they found is both elegant and puzzling. The expansion isn't slowing down as you might expect if gravity were the only force at play. Instead, it's accelerating. Galaxies are moving apart from each other faster and faster as time goes on. This acceleration appears to be driven by something called dark energy, a mysterious component of the universe that acts like anti-gravity, pushing space apart. Dark energy makes up about 68% of the universe's total energy content, dominating everything else, yet we have no idea what it actually is. But that's a mystery about the universe's current behaviour. What about the past? How did the expansion rate change over cosmic history? This is where observations of the distant universe become crucial, because remember, looking farther away means looking farther back in time. By measuring the properties of galaxies at different distances, we're essentially sampling the universe at different epochs and watching how its expansion has evolved. The picture that emerged from decades of observations was fairly clear. In the universe's earliest moments, space expanded extraordinarily rapidly in a process called cosmic inflation. Then, after inflation ended, the expansion continued, but at a much slower rate, gradually decelerating as gravity tried to pull everything back together. About 5 or 6 billion years ago, dark energy became dominant, and the expansion began accelerating again. A neat story. Fast at first, then slower, then faster again. But recent observations, including some from Webb and other cutting-edge telescopes, have hinted at something more complex. When astronomers measure the expansion rate of the universe using different methods, they don't always get exactly the same answer. One method looks at the cosmic microwave background, the faint afterglow of the Big Bang itself, and uses that to calculate how fast the universe should be expanding today. Another method measures distances to nearby supernovae and galaxies directly to determine the current expansion rate. But now, looking deeper and clearer than ever before, we're finding details that don't quite match expectations. Galaxies that form too soon, structures that assemble too quickly, expansion rates that might not line up perfectly across cosmic time. These aren't fatal flaws in our understanding. Science is robust enough to handle surprises, but they are reminders that the universe is under no obligation to be simple or to match our expectations. As we continue this journey, we'll see that this theme repeats. The edge of the universe is a place where our assumptions get tested, where the cosmos reveals aspects of itself we didn't anticipate. It's humbling, certainly, perhaps unsettling to our sense of having figured things out. But it's also deeply exciting because every surprise is an opportunity to learn something new, to refine our understanding, to glimpse aspects of reality we'd overlooked. And with that thought settling into your mind, let's move forward into our second act, where we'll explore what these distant observations tell us about the universe's composition and the mysterious dark components that dominate it. Everything you can see, every star and planet and galaxy and nebula, every bit of luminous matter in the entire universe makes up less than 5% of the cosmos's total mass and energy. The rest is invisible to our eyes and to our telescopes. Most of it is dark energy, that mysterious force accelerating the universe's expansion. But about 27% is something called dark matter, and it's this dark matter that concerns us now. Before we continue, I want to pause for just a moment, because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level, but you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. We know dark matter exists not because we've seen it directly, but because we can see its gravitational effects. Galaxies rotate faster than they should given only their visible matter. Galaxy clusters hold together more strongly than the gravity from their visible stars and gas can account for. The universe's large-scale structure, that cosmic web we discussed, requires far more mass than we can see to have formed the way it did. All these observations point to the presence of matter that doesn't emit, absorb, or reflect light. It doesn't interact with electromagnetic radiation at all, as far as we can tell. It simply exists, exerting gravity, shaping the cosmos, and remaining frustratingly invisible to every instrument we've built to detect it directly. Dozens of experiments around the world are searching for dark matter particles, trying to catch them interacting with ordinary matter in underground detectors. So far, despite decades of effort, no definitive detection has been made. But while we wait for direct detection, we can study dark matter's effects. And one of the most powerful ways to do that is by looking at the distant universe, back to epochs when the cosmos was simpler and dark matter's influence might be easier to isolate and understand. In the early universe, dark matter played a crucial role. Those tiny density variations that eventually became the cosmic web started as variations in the distribution of dark matter. Dark matter began clumping together first, and its gravity pulled ordinary matter into the same regions. Where dark matter collected, galaxies eventually formed. The pattern of dark matter clumping determined where structures would emerge and how quickly they'd grow. Observations of the distant universe can tell us about this process. By mapping where early galaxies formed and how they clustered together, we're essentially mapping the underlying dark matter distribution. The galaxies are like lights revealing an otherwise invisible landscape, and what this mapping reveals is both consistent with our dark matter theories and, in some details, slightly puzzling. One particular observation stands out. Astronomers have studied what's called gravitational lensing, using distant galaxies and quasars. When light from a very distant object passes near a massive concentration of matter, that matter's gravity bends the light's path. The distant object appears distorted, sometimes stretched into arcs or even multiplied into several images. It's like looking through a cosmic magnifying glass. By studying these lensing effects, astronomers can map the distribution of mass along the light's path, including the dark matter. They've done this for countless distant galaxies, building up statistical pictures of how dark matter was distributed in the early universe. Most of the results match expectations beautifully. The dark matter is where it should be, doing what it should do, But there are some observations, a minority but a persistent one, that show more lensing than expected. It's as if there are small, dense clumps of dark matter scattered around, concentrating gravity in ways that produce stronger lensing than the smooth distribution predicted by theory. These clumps, if they're real, and not some artifact of the analysis, might tell us something about dark matter's properties. One possibility is that dark matter is slightly more clumpy, more concentrated into small halos than our standard models predict. This could happen if dark matter particles interact with each other slightly, not through electromagnetism, but through some other force we don't know about yet. These interactions, rare as they might be, could cause dark matter to cool and condense in ways that affect its distribution. Another possibility is that we're seeing the signatures of primordial black holes, objects that formed in the very early universe from extreme density fluctuations. Some theories suggest that dark matter might partly consist of these ancient black holes, ranging from tiny masses to hundreds of times the mass of our Sun. If they exist, they'd create exactly the kind of concentrated mass that could produce the excess lensing some observations suggest. These ideas remain speculative, the evidence isn't overwhelming, and other explanations for the observations exist. But this is exactly the kind of question that observations at the edge of the universe can help answer. The early cosmos provides a simpler laboratory, a place where the competing effects that confuse modern observations are less prominent. If dark matter behaves unexpectedly, those unexpected behaviours might stand out more clearly against the simpler backdrop of the young universe. There's something almost philosophical about dark matter when you really think about it. We're surrounded by this substance. It permeates space, flows through our galaxy, passes through Earth and through our bodies by the trillions every second, and we can't feel it, or see it, or touch it. It's there, fundamentally shaping the universe, and yet completely inaccessible to our normal senses, or even to our most sophisticated electromagnetic instruments. The only reason we know it exists at all is because of gravity, that universal force that affects all matter and energy. Gravity doesn't care whether something emits light. It doesn't distinguish between visible and invisible. It simply responds to mass and energy, pulling everything together, shaping orbits and trajectories in the grand architecture of the cosmos. And it's through gravity that we've glimpsed dark matter's influence, even if the substance itself remains mysterious. As we continue mapping the early universe with increasingly powerful telescopes, we're also mapping dark matter's history. We're learning how it clumped and clustered, how its distribution evolved, how it created the conditions for galaxies and stars and eventually life to emerge. Every observation of a distant galaxy carries information about the dark matter in and around it. Every measurement of cosmic structure tells us something about the invisible scaffold on which that structure built itself. And this leads us to consider something closely related, another invisible component of the cosmos that reveals itself only through indirect means. If dark matter is mysterious, this next topic is even more so, because while dark matter at least behaves like matter, dark energy behaves like nothing we've ever encountered in any laboratory or anywhere else in nature. Imagine you throw a ball into the air. It rises, slows, stops, and falls back down. Gravity pulls it back. Now imagine you throw a ball upward, and instead of slowing down, it speeds up. It accelerates away from Earth, faster and faster, until it vanishes into space. That would violate everything we know about gravity. It would be deeply wrong according to the physics that has worked perfectly for centuries. Yet this is essentially what the universe is doing. Galaxies are moving apart, and instead of that motion slowing down as gravity tries to pull everything back together, it's speeding up. The universe's expansion is accelerating, and this acceleration requires something that acts like anti-gravity, a repulsive force that pushes space apart. We call this dark energy, and it makes up the majority of everything that exists. The discovery of cosmic acceleration came in the late 1990s from observations of distant supernovae. Two independent teams of astronomers were trying to measure how much the universe's expansion had slowed down over time. They expected to find deceleration, a universe whose expansion was gradually breaking. Instead, they found acceleration. The finding was so unexpected that both teams initially thought they'd made a mistake, but the data held up, additional observations confirmed it, and in 2011 the discovery earned its leaders the Nobel Prize in Physics. Since then, astronomers have measured the acceleration in multiple independent ways, all confirming the same basic picture. The universe's expansion is speeding up, driven by this mysterious dark energy. And the most distant observations, those looking back billions of years to when the universe was younger, show us when this acceleration began. For the first several billion years after the Big Bang, the universe's expansion was indeed slowing down. Gravity was winning, pulling matter together, trying to overcome the initial outward push from the Big Bang. But about 5 or 6 billion years ago, something changed. The universe had expanded and thinned out enough that matter's gravity became less dominant. Dark energy, which had always been there but was less important when matter was denser, began to take over. And once it did, the expansion started accelerating. Observations of distant galaxies and quasars let us trace this transition. By measuring precisely how far away these objects are and how fast they're receding from us, we can reconstruct the expansion history of the universe. We can watch, epoch by epoch, as deceleration gave way to acceleration. It's like watching a video of cosmic history, seeing the moment when the universe's fate shifted from potentially recollapsing to definitely expanding forever. But here's where things get strange, where these disturbing elements begin to creep in. We don't know what dark energy is. We genuinely don't. We've given it a name, measured its effects, determined that it makes up about 68% of the universe's total energy density, and we still have no idea what it actually represents. The simplest explanation is that dark energy is the cosmological constant, an inherent energy of space itself. According to quantum field theory, even empty space isn't truly empty. It seethes with virtual particles popping into and out of existence, a quantum foam of temporary fluctuations. This quantum vacuum should have an energy associated with it, and that energy would act exactly like dark energy, pushing space apart. The problem is when physicists calculate what the vacuum energy should be based on quantum theory, they get a number that's wrong by a factor of about 10 to the power of 120. That's one followed by 120 zeros. It's not just wrong, it's spectacularly, cosmically wrong, perhaps the worst prediction in the history of physics. Something fundamental is missing in our understanding, some principle or mechanism that determines the actual value of vacuum energy and makes it far smaller than naive calculations suggest. Other explanations for dark energy have been proposed. Maybe it's not a constant, but a field that can vary over time. Something called quintessence. Maybe it's a sign that Einstein's theory of gravity needs modification on cosmological scales. Maybe it's evidence for extra dimensions of space beyond the 3 we experience. Each possibility leads down complex theoretical paths, and none have gained definitive support from observations yet. What does the edge of the universe tell us about all this? Well, by observing the most distant galaxies and quasars, we can test whether dark energy has remained constant over time or whether its strength has changed. If dark energy is truly Einstein's cosmological constant, it should be absolutely constant throughout cosmic history. If it's something more exotic like quintessence, it might have varied. The observations are challenging because measuring distances accurately in cosmology is notoriously difficult. But the data we have so far suggests dark energy has been fairly constant, at least over the past several billion years. There are hints from some analyses that it might have varied slightly, but these hints are tentative and could easily disappear with better data. Most of the evidence supports the constant picture. Frustrating as that might be, given how little we understand about what that constant actually represents. There's a deeper philosophical discomfort here that's worth acknowledging. For most of human history, we assumed the universe was made of stuff we understood. Earth, water, air, fire, atoms and molecules, stars and galaxies composed of familiar matter, behaving according to familiar rules. Even when we discovered quantum mechanics and relativity, strange as they were, they dealt with matter and energy we could experiment with, detect, measure in laboratories. But now we find ourselves in a cosmos where 95% of everything is made of substances we can't see and don't understand. Dark matter and dark energy dominate the universe, determine its structure and fate, and remain fundamentally mysterious despite decades of intensive research. It's humbling. It's unsettling. It forces us to acknowledge how little we actually know about the cosmos we inhabit. Yet there's beauty in this ignorance too. These mysteries represent frontiers, opportunities for discovery, chances to learn something genuinely new about nature. Every generation of scientists has faced questions they couldn't answer with the knowledge and technology available to them. Ours faces the mystery of the dark universe. Future generations might look back and wonder how we could have been puzzled by something that seems obvious to them, just as we wonder how physicists a century ago failed to discover dark matter and dark energy, despite having all the observational tools they needed. The edge of the universe, those distant regions where we see cosmic history unfolding in its earliest chapters, offers our best chance to crack these mysteries. The conditions there were different, simpler in some ways, more extreme in others. If dark energy behaves differently under those conditions, we might be able to detect it. If dark matter's properties stand out more clearly against the early universe's simpler backdrop, we might finally identify what it is. And this connects to our next topic. Another aspect of the distant universe that challenges our understanding and hints at physics we haven't fully grasped. Because beyond just dark matter and dark energy, the earliest galaxies show us something unexpected in their very chemistry, in the elements they contain and the processes that created those elements. When you look at a star's light spread into a spectrum, you're seeing far more than just colours. You're seeing a chemical fingerprint. Every element absorbs and emits light at specific wavelengths, creating a unique pattern of dark and bright lines in the spectrum. By studying these patterns, astronomers can determine what a star is made of, even if that star is billions of light years away. This technique, called spectroscopy, is one of astronomy's most powerful tools. It tells us not just what distant objects are made of, but how hot they are, how fast they're moving, whether they're rotating, whether they have magnetic fields. An enormous amount of information is encoded in the light reaching our telescopes, and spectroscopy is how we decode it. In the early universe, we expected to find very simple chemistry. The Big Bang itself produced only the lightest elements: hydrogen, helium, and traces of lithium. Everything heavier than these, every atom of carbon and oxygen and iron and gold in your body, was created later, inside stars. Stars fuse hydrogen into helium in their cores, and more massive stars fuse helium into carbon, oxygen, and heavier elements still. When these massive stars explode as supernovae, they scatter these elements into space, enriching the gas that will form future generations of stars and planets. This process of stellar nucleosynthesis takes time. The first stars were made of nearly pure hydrogen and helium. Only after they lived and died could the next generation of stars form with any significant heavy element content. Each stellar generation adds to the universe's chemical enrichment, gradually increasing the concentration of elements like carbon, nitrogen, oxygen, silicon, iron. So when we look at the most distant, earliest galaxies, we expect to see very primitive chemistry. These galaxies should contain stars with almost no heavy elements, population 3 stars as astronomers call them, the first stellar generation. We've never actually observed a population 3 star directly, partly because they're so distant and faint, but we expect they existed and dominated the early universe. What Webb and other telescopes have found is more complex than this simple picture. Some early galaxies show signs of significant chemical enrichment already, with heavy elements present in concentrations that suggest multiple generations of stellar evolution have already occurred. Remember, these are galaxies we're seeing as they were when the universe was only a few 100 million years old. For them to already show heavy element enrichment means stellar evolution must have proceeded very quickly, faster perhaps than we thought possible. One particularly interesting observation involved detecting oxygen in distant galaxies. Oxygen is created in massive stars and expelled when those stars explode. Finding oxygen in an early galaxy tells us that massive stars have already formed, lived their brief lives, and died spectacularly, enriching their galaxy with newly created elements. It's a timeline compressed into what should be impossibly short periods. Now astronomers are careful to distinguish between different scenarios here. It's possible these galaxies aren't quite as distant as their initial estimates suggested. Distance measurements to very faint distant objects are challenging, and small errors can lead to significant revisions. As more data comes in, some of these surprisingly enriched early galaxies might turn out to be slightly younger than first thought, giving more time for chemical evolution to occur. But even accounting for these uncertainties, there's a pattern emerging. The early universe seems to have been chemically active more quickly than we expected. Star formation might have been more efficient. Massive stars might have been more common. The timescale for a galaxy to go through multiple stellar generations might be shorter than our models predict. There's also the intriguing possibility that the very first stars, those population 3 objects, were very different from anything we see today. Some theories suggest they could have been extremely massive, hundreds of times the mass of our Sun, living very brief lives and dying in unimaginably powerful explosions called pair instability supernovae. These hypothetical stellar giants would have been extraordinarily efficient at creating and dispersing heavy elements, potentially enriching their host galaxies much faster than the slower process of many smaller stars living and dying over millions of years. We haven't detected population 3 stars yet, but their signatures might be hidden in the spectra of early galaxies. Some researchers are looking for specific patterns that would indicate the influence of these hypothetical first stars, specific ratios of elements that couldn't be produced any other way. It's detective work at cosmic scales, trying to reconstruct what happened in the universe's earliest chapters from the faint clues encoded in ancient light. What makes this particularly fascinating is that chemical enrichment is what made planets like Earth possible. It's what made life possible. The carbon in your cells, the calcium in your bones, the iron in your blood, all were created in stars that lived and died long before our Sun formed. We are quite literally made of stardust, and the process that created our stardust, that produced the chemical diversity necessary for complex molecules and biology and consciousness, began in those earliest epochs, in the first generations of stars and galaxies. Understanding how quickly chemical enrichment occurred in the early universe helps us understand how common planets might be, how early in cosmic history planetary systems could have formed, whether there might have been worlds with the right chemistry for life emerging far earlier than we typically imagine. These aren't just abstract questions, they touch on fundamental issues about our place in the cosmos, about whether we're early arrivals in a universe just now becoming hospitable to life, or latecomers to a process that's been ongoing for most of cosmic history. The spectra of distant galaxies carry these answers, written in patterns of light and darkness across different wavelengths. Every spectrum tells a story of stellar birth and death, of elements created and dispersed, of chemistry growing richer generation by generation, and by reading these stories from the universe's earliest chapters, we're learning how the cosmos prepared itself for complexity, for planets, for life. This brings us naturally to consider another aspect of early galaxies that has surprised astronomers: They're central regions where supermassive black holes lurk. And the way these cosmic monsters seem to have grown to enormous sizes impossibly quickly in the young universe. At the centre of nearly every large galaxy, including our own Milky Way, sits a supermassive black hole. These objects contain millions or billions of times the mass of our Sun, compressed into a region smaller than our solar system. They're among the most extreme objects in the universe, places where gravity becomes so strong that not even light can escape. We've known about supermassive black holes for decades. We can detect them through their gravitational influence on nearby stars, which orbit the galactic centre at tremendous speeds, clearly responding to an enormous concentrated mass. We can see material spiralling into them, forming bright accretion disks that outshine entire galaxies. Some supermassive black holes power jets of matter and energy that extend for millions of light years, visible across the cosmos. What we didn't know, until recently, was how common these giants were in the early universe and how massive they had already become. And this is where observations of the distant universe have revealed something genuinely puzzling, something that challenges our understanding of how black holes grow. Black holes grow by consuming matter. They pull in gas and dust and stars, adding that mass to themselves, getting larger and more massive. But there's a limit to how fast they can grow. Pushes against incoming material, counteracting gravity. This creates a balance, limiting the rate at which the black hole can consume new matter. This limit is called the Eddington limit, named after the astronomer Arthur Eddington who first described it. It means that even in ideal conditions, a black hole can only grow so fast. Double its mass in a certain amount of time, and that time depends on how much matter is available and how efficiently the black hole can consume it without the radiation blowing everything away. Using these principles, astronomers can calculate how long it should take for a supermassive black hole to grow from stellar mass, the size of a dead star, up to millions or billions of solar masses. The timeline is long, hundreds of millions to billions of years depending on conditions. Early in the universe, when the first black holes formed from the deaths of the first massive stars, they should have been relatively small, perhaps tens to hundreds of solar masses. Growing from there to supermassive status should take time. But when we observe the distant universe, when we look back to when the cosmos was less than 1 billion years old, we find supermassive black holes already in place. Some contain billions of solar masses. They're powering bright quasars, the most luminous objects in the universe, visible across billions of light years, and they shouldn't be there, or at least they shouldn't be so massive so early. One particularly striking example is a quasar discovered by Webb and other telescopes in a galaxy that existed when the universe was only about 700 million years old. Less than 5% of its current age, this quasar is powered by a black hole containing more than 1 billion times the mass of our Sun. To grow that large that quickly would require consuming matter essentially continuously at or above the Eddington limit from the moment the first stars died, with no breaks, no pauses, no periods of low accretion. It's theoretically possible, but it requires extremely optimized conditions. And this quasar isn't unique. Astronomers have found several supermassive black holes in the early universe, all presenting the same basic problem. They're too massive for their age. It suggests either that black holes can grow faster than the Eddington limit under certain conditions, or that they started larger than we thought, or that there's some other mechanism we haven't considered. One possibility is that the first black holes didn't form from dying stars at all. Maybe they formed directly from enormous clouds of gas collapsing in the early universe, creating black holes that started out already massive, thousands or tens of thousands of solar masses. These _(1) black holes would have a head start, making it easier to grow to supermassive status within the available time. Another idea is that early black holes had access to unusually rich supplies of gas. In the dense, chaotic environments of the early universe, with galaxies merging frequently and gas clouds colliding, black holes might have been able to consume matter at rates we don't see in the modern cosmos. This could push them above the Eddington limit temporarily, allowing faster growth. There's also speculation about exotic processes we don't fully understand. Maybe dark matter can be captured by black holes, adding mass in ways that don't produce the radiation that normally limits growth. Maybe there are other, more efficient accretion mechanisms in extreme environments. These ideas are more speculative, but they're being explored because the observations demand explanation. What makes this particularly interesting is that supermassive black holes appear to play an important role in galaxy evolution. They inject energy into their host galaxies through jets and winds, heating gas and affecting star formation. The mass of a galaxy's central black hole correlates with properties of the galaxy itself, suggesting a deep connection between black hole growth and galaxy growth. Understanding how these black holes formed and grew so quickly in the early universe helps us understand how galaxies themselves assembled and evolved. There's something almost unsettling about black holes in general, beyond just the early universe puzzle. They represent points where our physics breaks down, where the equations we use to describe nature give infinite answers and stop working. At a black hole's event horizon, time itself behaves strangely, appearing to stop from an outside observer's perspective. Inside the event horizon, we simply don't know what happens. General relativity and quantum mechanics, our two best theories of physics, give contradictory answers. Finding these objects in abundance in the early universe, already grown to tremendous sizes, adds another layer to the mystery. It suggests the universe had mechanisms for building extreme objects quickly, mechanisms we're still working to understand fully. Every supermassive black hole in a distant galaxy represents a puzzle, a question about growth rates and initial conditions, and the complex interplay between black holes and their host environments. As we continue observing these distant quasars and early galaxies, we're gathering data that will eventually answer these questions. We're measuring black hole masses more accurately, determining when they formed and how quickly they grew. We're looking for the signatures of different formation scenarios in the properties of early black holes and their hosts. Slowly, observation by observation, the picture will come into focus. But for now, there's an element of mystery, a sense that the universe's earliest epochs were more dynamic and violent and productive than we imagined. Black holes growing to billions of solar masses in cosmic eye blinks, galaxies forming with shocking rapidity, structure assembling at breakneck speeds. The young universe was a busy place, and we're still learning just how busy it was. This theme of unexpected activity, of things happening faster and more intensely than predicted, continues as we turn our attention to another surprising aspect of early galaxies, their star formation rates, the sheer abundance of stars being born in these young systems, and what that tells us about the universe's early productivity. Stars are born in clouds of gas and dust. When these clouds collapse under their own gravity, they fragment into clumps. And those clumps compress and heat until nuclear fusion ignites in their cores. This process, star formation, has been ongoing throughout cosmic history. It's how the universe transformed from a cloud of simple hydrogen and helium into the rich tapestry of stars and planets we see today. In the modern universe, we can watch star formation happening. We see stellar nurseries like the Orion Nebula, regions where hundreds of new stars are being born right now. We can measure how quickly stars are forming in different galaxies, a quantity called the star formation rate, and we've built up a good understanding of what controls star formation, what determines whether a galaxy produces many new stars or relatively few. Generally, star formation requires cold, dense gas. When gas is too hot or too diffuse, it doesn't collapse easily. Galaxies that have lots of cold gas can form stars rapidly. Galaxies that have exhausted their cold gas reservoirs or had that gas heated or blown away form stars slowly or not at all. Over cosmic time, we see a pattern. Star formation was very active in the early universe, peaked some 10 to 11 billion years ago, and has been declining ever since as galaxies consume their gas supplies. This pattern makes sense. Early galaxies had lots of pristine gas fresh from the Big Bang. They were actively growing through mergers and accretion. These are ideal conditions for star formation. As time went on, gas was locked up in stars or blown out of galaxies by supernovae and black hole activity. Star formation naturally declined as the fuel ran out. Observations of distant galaxies confirm this overall picture. When we look back several billion years, we see galaxies forming stars much more vigorously than most modern galaxies. But even within this expected pattern, there are surprises. Some early galaxies appear to have been forming stars at rates that seem unsustainably high, producing new stars at hundreds or even thousands of times the rate of the Milky Way today. Now, high star formation rates in the early universe aren't unexpected. What's surprising is just how high some of these rates appear to be, and how common very active star-forming galaxies seem to be at early epochs. It suggests the early universe was not just more active, but far more active than our models comfortably predicted. There's a particular class of galaxies called starburst galaxies. These are systems undergoing episodes of extraordinarily intense star formation, often triggered by galaxy mergers that funnel large amounts of gas into the central regions. In the modern universe, starburst galaxies are relatively rare. Most galaxies form stars at moderate steady rates. But in the early universe, starburst-like conditions might have been the norm rather than the exception. Webb's observations have revealed numerous early galaxies with extremely high star formation rates. Some appear to be forming stars so rapidly that they should exhaust their gas supplies in just a few tens of millions of years. This raises questions about sustainability. How can a galaxy maintain such furious star formation? Where does all the gas come from? What happens after the burst ends? One possibility is that early galaxies had access to larger reservoirs of cold gas than we typically assume. The universe was denser then, and gas could flow into galaxies more easily from the surrounding cosmic web. This constant supply of fresh fuel could maintain high star formation rates for extended periods, much longer than we'd expect for an isolated galaxy consuming a fixed supply of gas. Another factor might be the efficiency of star formation. Not all gas in a galaxy participates in star formation. Much of it might be too hot or too dispersed, but under certain conditions, perhaps more of a galaxy's gas can be converted into stars. If early galaxies were somehow more efficient at turning gas into stars, they could achieve higher star formation rates with the same amount of gas. There's also the question of what regulates star formation. In modern galaxies, several processes act to suppress or limit star formation. Supernova explosions blow gas out of galaxies or heat it up, making it harder to collapse into stars. Active galactic nuclei, powered by supermassive black holes, inject energy that can also suppress star formation. Radiation from young stars can heat and ionize surrounding gas, counteracting the cooling that's necessary for collapse. In the early universe, some of these regulatory mechanisms might have been less effective. Maybe there hadn't been enough time for feedback processes to develop. Maybe the conditions were just different in ways that allowed star formation to proceed more freely. This is an active area of research, trying to understand what controlled star formation in the universe's first billion years, and how that differed from the processes we observe in nearby galaxies today. What's particularly interesting is connecting these high star formation rates to the other puzzles we've discussed. If galaxies were forming stars extremely rapidly, that would help explain how they could become so massive so quickly. It would also explain the chemical enrichment, because rapid star formation means lots of massive stars being born, living briefly and dying, scattering heavy elements. It might even connect to the black hole growth problem, because intense star formation often goes hand in hand with black hole accretion. So perhaps what we're seeing is a consistent picture of an early universe that was simply more active, more dynamic, more productive than our models based largely on nearby observations had led us to expect. The universe hit the ground running, so to speak, transforming from a nearly uniform sea of hydrogen and helium into a complex, structured, chemically enriched cosmos in a remarkably short time. This realization is intellectually humbling. We'd built sophisticated models of cosmic evolution, run detailed computer simulations, and thought we understood the broad outlines of how the universe developed. And we do, for the most part. The basic physics is correct. The overall timeline is sound. But the details, the rates, the efficiencies, the specific mechanisms, these turn out to be more complex than we appreciated, and there's beauty in this complexity. The universe isn't simple. It doesn't follow the most straightforward path from initial conditions to final state. It's rich and varied, with different galaxies following different evolutionary paths, with feedback processes and interactions creating intricate patterns. Understanding this complexity, mapping it out, explaining it, is the work of science, and it's work that continues with every new observation from Webb and other cutting-edge telescopes. As we look toward the next portion of our journey, we'll shift perspective slightly. We've been focusing on what we see at the edge of the universe, on the surprising observations and the questions they raise. Now let's consider what it means to observe these distant realms, what limitations we face, and what fundamental physics determines what we can and cannot see when we look to the cosmic horizon and beyond. There's a boundary in the universe that we can never see beyond, no matter how powerful our telescopes become. It's not a physical barrier. There's no wall or edge of space. Instead, it's a limitation imposed by the finite age of the universe and the finite speed of light. We call it the cosmic horizon, and understanding it is key to understanding what we can and cannot know about the cosmos. Light travels at a constant speed, roughly 300,000 kilometers per second, or about 186,000 miles per second. This speed is fast by human standards. Light can circle Earth's equator more than 7 times in a single second. But on cosmic scales, light's speed is limiting. Even at this tremendous velocity, light takes time to cross vast distances. The observable universe is the region of space from which light has had time to reach us since the Big Bang. Because the universe is about 13.8 billion years old, you might think the observable universe extends 13.8 billion light years in all directions. But the universe has been expanding during all the time that light has been travelling, so the actual size is larger. The observable universe has a radius of about 46 billion light years. The total diameter is roughly 92 billion light years across. This is the cosmic horizon. Beyond this distance, light simply hasn't had enough time to reach us yet. The expansion of space has carried those regions so far away that their light, even though it's been travelling toward us since the beginning, hasn't arrived. And for the most distant regions, it may never arrive, because space is expanding faster than light can travel through it in those places. This is a profound limitation. It means there are regions of the universe we can never observe, never study, never know anything about through direct observation. They might contain galaxies, stars, planets, perhaps even life. But they're beyond the horizon, causally disconnected from us, existing in a part of the universe that might as well be a separate reality. Now, the horizon isn't static. As time passes and light from more distant regions reaches us, the horizon technically expands, but the universe's accelerating expansion complicates this. For regions beyond a certain distance, the expansion is so rapid that light emitted toward us today will never reach us. The horizon has, in a sense, stopped growing in those directions. We're locked into seeing a particular region of the cosmos, unable to peer beyond no matter how long we wait. This creates a strange situation. The universe might be infinite, extending forever in all directions, or it might be finite but without edges, curved back on itself like the surface of a sphere. We can't tell from observations alone which is true, because both infinite and sufficiently large finite universes look identical within our cosmic horizon. The geometry and topology of the cosmos on the larger scales remain unknown, and might remain forever unknowable if they exist beyond what we can observe. There's another aspect of the cosmic horizon that's worth contemplating. The most distant light we can observe comes from a time shortly after the Big Bang, when the universe was very young. But we can't see all the way back to the Big Bang itself. There's a barrier, a point earlier than which the universe was opaque to light. In the universe's first few 100,000 years, it was too hot and dense for light to travel freely. Any photon emitted was almost immediately absorbed by the sea of charged particles filling space. Light couldn't propagate. It was trapped. Only when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms did space become transparent. This moment, called recombination, occurred about 380,000 years after the Big Bang. The light released at recombination is still travelling through space. It's been stretched by cosmic expansion into microwaves, and we detect it as the cosmic microwave background, that faint glow coming from all directions in the sky. This is the oldest light in the universe, the earliest thing we can see electromagnetically. It forms a spherical shell around us, marking the moment when the universe became transparent. Before recombination, we cannot see with light. The universe was opaque, but perhaps we can observe those earlier moments through other means. Gravitational waves, ripples in space-time itself, can travel through opaque matter. If there was a source of gravitational waves in the very early universe, perhaps from violent processes in the first fractions of a second, those waves might still be detectable today, carrying information from epochs earlier than anything light can show us. Scientists are developing increasingly sensitive gravitational wave detectors, hoping to catch these primordial signals. If successful, it would open a window into the universe's first moments, pushing our horizon back from 380,000 years to mere instants after the Big Bang. It's a tantalizing prospect, the chance to observe the universe's birth directly, rather than inferring it from later evidence. But even gravitational waves have their limits. There's likely an ultimate horizon, a point before which the universe was so extreme that no signal of any kind could propagate to us. This might be the Planck epoch, the first 10 to the minus 43 seconds after the Big Bang, when quantum effects dominated and our current theories of physics break down. Beyond that barrier, we might never be able to observe directly. We can theorize, calculate, extrapolate. But direct observational confirmation might be impossible. This is both humbling and liberating. Humbling because it reminds us that there are fundamental limits to knowledge, boundaries we cannot cross no matter our ingenuity. Liberating because it focuses our attention on what we can observe, on the vast universe that lies within our horizon, full of mysteries and wonders waiting to be explored. The edge of the universe we've been discussing throughout this journey is really the edge of the observable universe. It's not an edge in space, but an edge in time, the most distant things we can see because their light has had just enough time to reach us. And what we find at this edge, in these most ancient and remote regions, challenges and surprises and delights us. But it also raises questions about what lies beyond. If we see galaxies at the cosmic horizon, there are surely more galaxies beyond it, similar in nature but forever hidden from view. The universe doesn't end at our horizon. It likely extends much farther, perhaps infinitely. We occupy a particular location in space and time, able to observe a particular bubble of the cosmos, and we must make peace with the fact that vast realms exist beyond our ability to study them. Yet within our observational reach lies an almost incomprehensible wealth of information. Trillions of galaxies, each containing billions of stars, spread across billions of light years. Structures that formed over billions of years of cosmic evolution. Chemistry that developed through countless stellar generations. The history of the universe from nearly the beginning to the present moment, all encoded in the light reaching our telescopes. We have more than enough to study, more than enough to challenge our understanding and inspire our wonder. And this brings us to consider another limitation, one imposed not by the speed of light but by the nature of light itself, and how it interacts with matter across cosmic distances. When we observe distant galaxies, we're not seeing them as they truly are. We're seeing them as they were billions of years ago, and we're seeing their light transformed by the journey it has taken to reach us. Understanding this transformation, this redshift, is crucial to interpreting what the edge of the universe tells us. Imagine a wave on the ocean. As it passes, you can measure the distance between wave crests. The wavelength. Now imagine that ocean is stretching as the wave travels across it, pulling the wave crests farther apart. The wave's wavelength increases during its journey. This is essentially what happens to light in an expanding universe. When light leaves a distant galaxy, it has a particular wavelength determined by whatever emitted it. An electron dropping between energy levels in a hydrogen atom, for instance, emits light at a very specific wavelength in the visible spectrum, producing a bright red line. But as that light travels through expanding space, the expansion stretches the light itself. The wavelength increases, shifting toward the red end of the spectrum and beyond into the infrared. The amount of stretching depends on how much the universe has expanded during the light's journey. Light from a nearby galaxy is barely redshifted at all because space hasn't expanded much in the short time the light took to arrive. But light from a galaxy billions of light years away has been travelling for billions of years, during which the universe has expanded substantially. That light is severely redshifted, perhaps stretched by factors of 10 or more, shifted from visible wavelengths deep into the infrared. Astronomers quantify this with a number called redshift, denoted by the letter Z. A redshift of 0 means no shift. The object is at rest relative to us, or so close that expansion effects are negligible. A redshift of 1 means wavelengths have been doubled by expansion. A redshift of 2 means wavelengths have been tripled. The highest redshifts observed by Webb and other telescopes exceed 10, meaning wavelengths have been stretched by more than a factor of 11. These high redshifts correspond to early cosmic times. A galaxy at redshift 10 is seen as it was when the universe was only about 480 million years old, less than 4% of its current age. The most distant galaxies detected by Webb have redshifts around 12 or 13, pushing into the universe's first few 100 million years. These are the objects at the edge of our observational reach, the ones showing us the universe in its infancy. But redshift complicates observation in important ways. Light that left a distant galaxy in the ultraviolet has been shifted into the visible by the time it reaches us. Light that left in the visible has shifted into the infrared. To see what a distant galaxy actually looks like, to study its spectrum and understand its properties, we need to observe at the redshifted wavelengths, which for the most distant objects means we need infrared telescopes like Webb. This is why Hubble, which observes primarily in visible and near-infrared light, couldn't see the earliest galaxies as well as Webb can. The light from those galaxies has been shifted too far into the infrared for Hubble's instruments to detect effectively. Webb, designed specifically for infrared observation, can see this ancient light clearly, opening the earliest chapters of cosmic history to direct observation. Redshift also affects what we can learn about distant galaxies. When we observe a nearby galaxy, we can study spectral features across a wide range of wavelengths. We can see ultraviolet light from hot young stars, visible light from older populations, infrared light from dust and cooler stars. Each wavelength range tells us something different about the galaxy's properties, but for a distant galaxy at high redshift, the light we receive has all been shifted. What was emitted as ultraviolet is now visible. What was visible is now infrared. What was infrared is now in the far infrared, or even at longer wavelengths. This means we're not seeing the same mix of information we'd see from a nearby galaxy. We have to understand how the redshift affects the light and correct for it in our analysis. Moreover, redshift is cumulative. Light passing through the universe encounters various things along the way. Clouds of gas between galaxies, other galaxies, clusters of matter. Each encounter can affect the light, absorbing certain wavelengths, adding spectral features. By the time light from the most distant galaxies reaches us, it carries information not just from its source, but from everything it passed through during its billions-year journey. Astronomers have learned to read this accumulated information. The absorption features tell us about the intergalactic medium, the gas between galaxies, and how it has evolved over time. We can see when certain regions of the universe became ionized, when metals from stellar nucleosynthesis began to enrich intergalactic space. The light from distant quasars acts like a flashlight shining through the universe's history, and the shadows and colours in that light tell the story of cosmic evolution. There's a beautiful irony here. The very thing that makes distant observations difficult, the redshifting of light by cosmic expansion, is also proof of that expansion. It's a direct consequence of general relativity, of the dynamic space-time Einstein's equations describe. Every redshift measurement confirms that the universe is expanding, that space itself is growing, carrying galaxies apart, and redshift connects directly to distance and time. By measuring a galaxy's redshift, we can calculate how far away it is and when in cosmic history we're seeing it. The mathematics isn't simple because the expansion rate has changed over time, but it's well understood. Every distant galaxy becomes a timestamp, a marker of a particular epoch in the universe's evolution. This means our surveys of the deep universe aren't just catalogues of objects. They're histories, timelines showing how the cosmos has changed and developed. By studying galaxies at different redshifts, we're watching cosmic evolution unfold, seeing the universe grow from simplicity to complexity, from smooth to structured, from primitive chemistry to rich elemental diversity. The highest redshift galaxies, those at the edge of observation, are the most valuable in some ways. They show us the universe at its youngest, most pristine state. They're the closest we can get to observing the cosmic starting conditions. And what they show us, as we've discussed, is often surprising, challenging our models, prompting us to revise our understanding. But we must always remember that we're seeing these galaxies through the filter of redshift, through billions of years of cosmic expansion that has transformed their light. When we image a high redshift galaxy, we're not seeing blue and white light from stars. We're seeing infrared radiation that was originally ultraviolet, stretched and dimmed by expansion. The galaxy we observe is a ghost of its former self, a faded echo of its actual appearance. This is perhaps unsettling in a subtle way. We can never see the distant universe as it truly was, only as it appears after its light has been transformed by expansion. We can correct for the redshift mathematically. Reconstruct what the galaxy would have looked like at the time the light was emitted, but we're always working with translated, shifted, altered information. It's a reminder of our remove from what we study, of the barriers space and time impose between us and the objects of our investigation. Yet despite these limitations, despite the transformations and complications redshift introduces, we can still learn. We can still measure, analyse, understand. The tools of spectroscopy and photometry, the theories of cosmology and astrophysics, give us the means to decode the redshifted light, to extract truth from altered signals. It's a testament to human ingenuity and persistence, this ability to look across billions of light years and billions of years and still make sense of what we see. And this connects to our next consideration. Another way that light from distant sources is affected not by cosmic expansion, but by the matter it encounters along its journey. Space isn't empty. Even in the vast reaches between galaxies, there's matter. It's diffuse, often just a few atoms per cubic meter, but accumulated across billions of light years, it adds up. This intergalactic medium, as it's called, affects light passing through it, leaving fingerprints on the spectra of distant quasars and galaxies. In the early universe, the intergalactic medium was primarily neutral hydrogen. After the Big Bang, once the universe cooled enough for protons and electrons to combine, most of the universe's hydrogen was in this neutral state. Neutral hydrogen absorbs light at specific wavelengths, particularly a strong absorption feature called Lyman alpha, which corresponds to a specific electron transition in the hydrogen atom. As light from a distant quasar travels toward us, it passes through clouds and filaments of this neutral hydrogen. Each cloud absorbs light at the Lyman alpha wavelength, but because each cloud is at a different distance and therefore has a different redshift, the absorbed wavelength appears different to us. The result is a spectrum showing many absorption lines at different wavelengths, creating what's called the Lyman alpha forest, a series of dark lines interrupting the quasar's light. By studying this forest of absorption lines, astronomers can map the distribution of neutral hydrogen in the universe at different epochs. They can see where gas was concentrated, how it was distributed along the cosmic web's filaments. It's a powerful technique, using distant bright sources like cosmic flashlights to illuminate the otherwise invisible matter between galaxies. What makes this particularly interesting is that the intergalactic medium's properties changed over time. In the universe's first billion years or so, most 90 minutes, you've been here for 90 minutes, quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. In the universe's first billion years or so, most of the hydrogen was neutral. But then something happened called reionization. The first stars and galaxies began emitting intense ultraviolet radiation. This radiation was energetic enough to strip electrons from hydrogen atoms, ionizing the gas. Over time, expanding bubbles of ionized gas grew around each source of radiation, eventually merging until nearly all the hydrogen in the universe was ionized again, returning to a state similar to what existed before recombination, but at much lower temperatures. This epoch of reionization is one of the last major phase transitions in cosmic history, and it's one we're actively studying through observations of the distant universe. By looking at quasars at different redshifts, astronomers can see how the Lyman alpha forest changes. At low redshifts, corresponding to more recent cosmic times, the absorption is moderate, indicating most hydrogen is ionized with only occasional neutral clouds. At higher redshifts, going back earlier in time, the absorption increases, showing more neutral hydrogen. But at the highest redshifts, something dramatic happens. The spectrum becomes almost completely absorbed at wavelengths shorter than Lyman alpha. It's as if someone has drawn a dark curtain across part of the spectrum. This is called the Gunn-Peterson trough, and it indicates that the light has passed through a universe where essentially all the hydrogen is neutral, absorbing the quasar's light almost completely. Finding the redshift where the Gunn-Peterson trough appears tells us approximately when reionization ended. We can watch, through these spectra, as the universe transitions from mostly neutral to mostly ionized. It's an extraordinary view of a cosmic phase transition, a moment when the character of the universe fundamentally changed. Recent observations with Webb and other telescopes have pushed these measurements to higher and higher redshifts, earlier and earlier times. We're seeing quasars and galaxies from epochs when reionization was still ongoing, when bubbles of ionized gas were expanding and merging. Some observations show variations in the absorption, suggesting we're seeing the patchy nature of reionization, different regions ionizing at different times depending on local conditions. This patchiness is important because it tells us about the sources of reionization. Were the first stars sufficient to ionize the universe, or did it require the contribution of the first quasars? How long did reionization take? Did it proceed uniformly, or were there regions that remained neutral longer than others? These questions are central to understanding the universe's first billion years, and the answers are being written in the spectra of distant bright sources. But the intergalactic medium doesn't just absorb light, it can also scatter and distort it. As light passes through regions of slightly higher or lower density, its path bends subtly. These gravitational lensing effects are usually small for the diffuse intergalactic medium, but they add up over billions of light years. The cumulative effect is a slight blurring of distant sources, a cosmic smearing that affects the sharpness of the images we obtain. There's also the question of dust. Not all the matter between galaxies is gas. Some of it is tiny solid particles, dust grains formed in stellar atmospheres, and supernova ejections and ejected into intergalactic space. Dust absorbs and scatters light, particularly blue light, making distant sources appear redder than they actually are. This can complicate our measurements, adding uncertainty to our estimates of distances and properties. Astronomers have developed sophisticated techniques to account for these effects. They model the intergalactic medium's absorption, correct for dust reddening, use multiple wavelengths to cross-check their results. But there's always some uncertainty, some residual effect that's hard to quantify perfectly. The universe between us and distant galaxies isn't quite transparent, isn't quite uniform, and we must account for this in our analysis. There's something almost poetic about the intergalactic medium's effects on light. Every photon that reaches our telescopes has a story, a journey through space spanning billions of years and billions of light years. Along the way, it encountered clouds of gas, passed near clusters of galaxies, was gravitationally deflected by concentrations of dark matter, perhaps was scattered by dust grains. All these interactions left marks, subtle alterations to the photon's energy and direction. We're not just receiving light from distant sources, we're receiving messages, information encoded in photons that have traversed the universe's history. And by reading these messages carefully, accounting for all the effects of the journey, we can reconstruct what the source was like and what the universe between us and the source contained. It's cosmic archaeology, reading ancient history and present observations. This idea of light as messenger, carrying information across time and space, is fundamental to astronomy. We cannot travel to distant galaxies. We cannot visit the early universe. All we have are the photons that reach us, and everything we know about the cosmos comes from decoding the information those photons carry. It's a humbling realization, this dependence on light, this reliance on electromagnetic radiation to reveal the universe. Yet it's also empowering. Light is universal. The same photons that allow us to see our immediate surroundings also bring us news from the edge of the observable universe. The same physics that governs how light interacts with matter in a laboratory here on Earth also governed those interactions billions of years ago in distant galaxies. We can trust that the patterns we see, the spectral lines and redshifts and absorptions, continue deeper into our exploration. Let's turn our attention to another aspect of observing the distant universe, one that's both a challenge and an opportunity. The fact that the most distant galaxies are often magnified and distorted by the gravity of intervening matter. Einstein's general relativity tells us that mass curves space-time, and this curvature affects how light travels. When light from a distant object passes near a massive concentration of matter, its path bends, following the curved space-time around the mass. This effect is called gravitational lensing, and it's one of the most powerful tools we have for studying both the distant universe and the matter distribution between us and distant sources. There are different types of gravitational lensing depending on the geometry and mass involved. Strong lensing occurs when light passes very close to a massive object like a galaxy cluster. The bending is so severe that multiple images of the background source appear, sometimes stretched into arcs or even complete rings called Einstein rings. Weak lensing is more subtle, a slight distortion of background galaxies' shapes that's only detectable statistically by studying many sources. For observing the most distant galaxies, strong lensing by galaxy clusters is particularly valuable. These clusters contain hundreds or thousands of galaxies bound together by gravity, along with vast amounts of dark matter. Their total mass is enormous, typically hundreds of trillions of times the mass of our Sun. This mass creates a powerful gravitational lens that can magnify and brighten background galaxies, making them easier to observe. The Hubble Space Telescope and now the James Webb Space Telescope have observed numerous galaxy clusters specifically to use them as natural telescopes. By pointing at clusters, astronomers can see magnified views of galaxies behind them, including some of the most distant galaxies known. These background galaxies appear brighter and larger than they would if we observed them directly, allowing detailed study that would be impossible otherwise. One particularly famous example is the galaxy cluster MAX J0416, which has been extensively studied by both Hubble and Webb. This cluster has lensed dozens of background galaxies, stretching some into long arcs and creating multiple images of others. By analysing these lensed images and modelling the cluster's mass distribution, astronomers can determine the distances and properties of the background galaxies with impressive precision. But lensing does more than just magnify, it also distorts. The shape of a lensed galaxy doesn't represent its true shape, but rather a stretched and warped version, determined by the specific geometry of the lensing. To understand what the galaxy actually looks like, we need to reverse the lensing effect, essentially undistorting the image using models of the cluster's mass distribution. But even with these cautions, lensing remains invaluable. For some of the most distant galaxies, it's the only way we can see them in detail. And as we develop better models, better computational techniques, better understanding of cluster mass distributions, the uncertainties decrease, and our confidence in the results increases. There's also a future promise in lensing. As we discover more lensing clusters and study them in detail, we're building up a catalogue of natural telescopes scattered across the sky. Future observations can target these clusters deliberately, knowing that they'll provide magnified views of whatever lies behind them. It's a resource that keeps giving, because there are always fainter, more distant background sources waiting to be discovered, and occasionally lensing produces spectacular surprises. Sometimes a supernova in a distant lensed galaxy gets magnified and brightened, allowing detailed study of stellar explosions from epochs when the universe was young. Sometimes a particularly rare or unusual galaxy gets lensed, bringing it within observational reach. The serendipity of lensing, the chance alignments that create these magnified views, has contributed enormously to our understanding of the distant universe. As we think about what lensing reveals, we're reminded again of the interconnected nature of cosmic observation. We use nearby clusters to study distant galaxies. We use distant galaxies to map dark matter. We use dark matter distributions to model lensing. Everything informs everything else, each observation contributing to a larger, more complete picture of how the universe is structured and how it has evolved. And this brings us naturally to consider what all these observations, lensed and unlensed, redshifted and corrected, tell us about the large-scale patterns in the universe, the organisation of matter into structures that span the cosmos. If you could see the universe from impossibly far away, from a vantage point outside the observable cosmos looking in, you'd notice patterns. Galaxies aren't scattered randomly. They cluster together. These clusters connect along filaments. Between the filaments lie voids, regions with very few galaxies. The overall structure resembles a cosmic web, a three-dimensional network of matter spanning billions of light years. We've known about this large-scale structure for decades from surveys of nearby galaxies, but extending these surveys to greater and greater distances, looking at the universe at earlier and earlier times, has revealed how this structure developed. And what we're finding is that the patterns we see locally extend deep into the past, back to epochs when the universe was less than 1 billion years old. The cosmic web forms because of gravity. In the early universe, matter was distributed almost uniformly, but not quite. there were tiny variations, regions that were slightly denser, and regions that were slightly less dense. These variations were set down in the universe's first moments, perhaps during cosmic inflation, and they provided the seeds for all future structure. Gravity amplifies these initial density variations. Regions that were slightly denser pulled in more matter, becoming denser still. Regions that were less dense lost matter to their denser neighbours, becoming voids. Over time, this process carved the universe into the web-like structure we see today, matter concentrated along filaments, with galaxy clusters forming at the nodes where filaments intersect. The patterns we observe at the edge of the universe, those early filaments and protoclusters, are the ancestors of the structures we see nearby. The cosmic web that surrounds us today was already beginning to form when the universe was less than 1 billion years old. Our own galaxy, our solar system, we ourselves, are products of that ancient web building. Participants in a process that started nearly 14 billion years ago. As we move into the fourth act of our journey, we'll shift from discussing what we observe to contemplating what it means. We've seen surprising galaxies, unexpected structures, mysterious dark components. Now let's consider what these observations tell us about our place in the cosmos and about the questions that remain. Science is often portrayed as a process of finding answers. We ask questions, perform experiments or observations, and determine what's true. But in reality, science is just as much about discovering new questions, realizing there are things we didn't know, finding mysteries where we thought there was certainty. The observations we've been discussing throughout this journey have certainly provided answers. We now know what the universe looked like in its first 1 billion years. We know galaxies formed earlier than we once thought possible. We know the cosmic web assembled quickly. We know supermassive black holes existed at surprisingly early times. These are real pieces of knowledge, facts about the cosmos we didn't have before Webb and other cutting-edge telescopes revealed them. But alongside these answers have come new questions. Why did galaxies form so quickly? What physical processes allowed such rapid growth? How did black holes reach supermassive status so early? What does the early assembly of structure tell us about the nature of dark matter? Each answer spawns new questions. And some of these questions touch on fundamental aspects of physics we don't yet understand. Consider the question of dark matter's nature. We know it exists. We've measured its effects in countless ways. We know roughly how much there is and how it's distributed. But we don't know what it is. Decades of experiments have failed to directly detect dark matter particles despite heroic efforts and increasingly sensitive instruments. The observations of early structure might provide clues. If dark matter behaves unexpectedly at early times or in dense environments, that could point toward particular theoretical models. Maybe dark matter particles can annihilate each other, producing signals we could detect. Maybe they decay over time, having been more abundant in the early universe than today. Maybe they have slight interactions we've overlooked. But equally, the observations might be consistent with multiple dark matter models, unable to distinguish between them. This is frustrating. We have this vitally important component of the universe, and we can't definitively say whether it's made of WIMPs or axions or sterile neutrinos or primordial black holes or something else entirely. The uncertainty gnaws at our understanding. A gap at the heart of our cosmological model. Or consider dark energy. We know even less about it than about dark matter. At least with dark matter we have candidate particles from particle physics theory. With dark energy, we don't even have particularly compelling candidates. It might be Einstein's cosmological constant, a property of space itself. It might be a dynamic field. It might be a sign that gravity behaves differently on cosmic scales than Einstein predicted. The distant universe provides some constraints. By measuring how the universe's expansion has changed over time, we can test whether dark energy has been constant or variable. So far, the evidence suggests constancy, but with significant uncertainties. Future observations with more sensitive instruments might narrow these uncertainties. but it's equally possible they'll just reveal new complications, new subtleties in how dark energy affects cosmic expansion. And then there are the truly deep questions, the ones that touch on why the universe is the way it is rather than some other way. Why do the fundamental constants of nature have the values they do? Why is the cosmological constant so small compared to what quantum theory predicts? Why did the universe start in such a low entropy state, allowing for the emergence of complexity over time? Why is there something rather than nothing? These questions venture into philosophy as much as physics. They might not have answers in the conventional sense, or the answers might require frameworks and concepts we haven't developed yet. String theory, multiverse concepts, anthropic reasoning, these are attempts to grapple with such questions, but they remain speculative, difficult to test observationally. Observations of the distant universe can't directly answer why the universe exists or why it has particular properties, but they can constrain possibilities. They can show us what the universe is actually like, what conditions held in its earliest moments, how things unfolded, and from these constraints, theorists can work to develop and test different explanatory frameworks. There's a humility required here, an acceptance that we might never have complete answers to some questions. The universe doesn't owe us comprehensibility. The fact that we can understand as much as we do, that the cosmos operates according to laws we can discover and test, is already remarkable. That some aspects remain mysterious, perhaps fundamentally so, is simply the nature of reality. Yet this doesn't mean we give up. Every question we can answer, every mystery we can resolve, expands our knowledge and often reveals new vistas of inquiry. The unknown isn't a wall blocking progress. It's a frontier inviting exploration, and the observations from the edge of the universe, showing us the cosmos in its earliest accessible epochs, represent one of the most distant frontiers we can currently probe. What's particularly interesting is how observations and theory interact in this process of discovery. Theorists make predictions based on their models and understanding of physics. Observers test those predictions, seeing if the universe actually behaves as predicted. Sometimes the predictions are confirmed, strengthening our confidence in the theories. Sometimes the observations surprise us, showing behaviour we didn't expect. These surprises are crucial. They're how we learn where our understanding is incomplete. If observations always perfectly match predictions, we'd learn nothing new. It's the discrepancies, the anomalies, the unexpected findings that drive progress. They tell us where to look for new physics, what aspects of our models need refinement. The distant universe has provided its share of surprises, galaxies that formed too quickly, structures that assembled too early, black holes that grew too fast. These aren't crises for cosmology, they're opportunities. They're signposts pointing toward deeper understanding, hints that there's more to learn about how the universe works. It explains an enormous range of observations. It explains an enormous range of observations spanning from the first fraction of a second after the universe's birth to the present day. It's passed countless tests. It's predicted phenomena that were later confirmed. But it's not complete. No scientific theory ever is. There are always edge cases, always new observations pushing beyond what we've tested before, always deeper questions lurking. The goal isn't to have all answers. The goal is to have a framework robust enough to make meaningful predictions, while flexible enough to incorporate new discoveries. As we continue our journey, let's consider what these distant observations tell us about one of the most profound questions we can ask. Are we alone in the universe? How do the conditions we observe at cosmic dawn relate to the possibility of life emerging elsewhere in the cosmos? Life, at least the kind we know, requires certain ingredients. It needs carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. It needs liquid water. It needs energy sources and some degree of chemical complexity. None of these existed in the immediate aftermath of the Big Bang. They had to be created, assembled, brought together through cosmic processes spanning billions of years. We've already discussed how elements heavier than hydrogen and helium are created in stars. Carbon forms in the cores of massive stars. Oxygen is produced when those stars later fuse carbon. Nitrogen, phosphorus, sulfur, iron, all the elements essential for life and for the rocky planets that might harbour it, come from stellar nucleosynthesis and the explosive deaths of stars. This means life requires at least one, probably multiple, generations of stellar evolution. The first stars, made of pure hydrogen and helium, couldn't have rocky planets around them. There wasn't enough heavy element material to form solid worlds. Only after those first stars died and seeded space with heavier elements could subsequent stars form with protoplanetary disks rich enough in heavy elements to create planets like Earth. How long did this take? When in cosmic history did the universe become chemically capable of supporting life? These questions connect directly to observations of distant galaxies and their chemical composition. As we've seen, some early galaxies show surprising chemical enrichment. They contain oxygen, carbon, and other heavy elements despite existing when the universe was only a few 100 million years old. This suggests stellar evolution proceeded quickly in these systems, cycling through multiple generations of stars in what seems like a short time. If chemical enrichment happened so rapidly, it means the universe became capable of forming rocky planets earlier than we might have expected. Perhaps the first Earth-like worlds formed not billions of years after the Big Bang, but only hundreds of millions of years after, as soon as the first galaxies had completed a few cycles of star formation and supernova enrichment. This is speculation, of course. Just because heavy elements existed doesn't mean Earth-like planets formed. Planets require not just the right chemistry, but the right conditions: stable stellar systems, appropriate orbits, protection from excessive radiation and impacts. Early galaxies might have been too chaotic, too active, too violent for stable planetary systems to survive long enough for life to emerge. That's us. We're the universe looking at itself, matter examining matter across cosmic distances and times. Whether we're unique or common, isolated or one of many, we're a product of cosmic evolution, participants in a process that started at the Big Bang and continues today. This realization is both humbling and elevating. Humbling because we're such a tiny part of an incomprehensibly vast cosmos. Elevating because we're capable of understanding that cosmos, of tracing our origins back to the beginning, of reading the universe's history in the light from distant galaxies. And this leads us to consider another dimension of our relationship with the cosmos, the way observations of the distant universe affect our philosophical and emotional understanding of existence and our place within it. There's something emotionally profound about seeing light that has travelled for 13 billion years. When you look at an image from the James Webb Space Telescope showing galaxies at the edge of the observable universe, you're not just seeing distant objects. You're seeing the past. You're seeing the universe as it was when it was young, when your galaxy didn't exist, when the chemistry that would eventually form your body hadn't been created yet. This connection across time can feel almost overwhelming. The light that entered Webb's mirrors left those galaxies billions of years before Earth existed. It travelled through expanding space, crossing an unimaginable distance, arriving at our solar system at just the right moment to be captured by our telescope. And we're here, ephemeral beings on a small planet, able to decode that ancient light and understand what it reveals. It's a privilege we often don't fully appreciate. For most of human history, the night sky was mysterious, beautiful but incomprehensible. Our ancestors saw the same stars we see, but had no way to know what they were, how far away, how old. They created myths and stories to explain the lights in the sky, imagination filling the space where knowledge couldn't reach. Now we know. We know stars are distant suns. We know galaxies are vast collections of stars. We know the universe had a beginning and has been evolving ever since. We know how old it is, how large, what it contains. We've built a scientific framework that connects the tiny scale of human experience to the cosmic scale of galaxies and eons. But with this knowledge comes a certain weight. Understanding cosmic distances and timescales can make human concerns feel insignificant. What does any of our daily drama matter against the backdrop of billions of galaxies evolving over billions of years? How can our individual lives have meaning when we're such temporary tiny phenomena in a universe so vast and ancient? These are questions humans have always grappled with, but modern cosmology gives them sharper focus. We can quantify our insignificance now. We can calculate that Earth is one planet among billions in our galaxy, which is one galaxy among trillions in the observable universe. We can determine that human civilization has existed for perhaps 10,000 years out of the universe's 13.8 billion, a fleeting moment in cosmic history. Some find this perspective liberating. If nothing we do matters cosmically, then we're free to create our own meaning, to value what we choose without worrying about some grand cosmic significance. The universe is indifferent, but that indifference is freedom. Others find it troubling or even disturbing, a cold reality that strips away comfortable illusions. We want to matter. We want our lives to have significance beyond just our subjective experience. Discovering we're cosmically insignificant can feel like a loss. But there's another way to think about this. Yes, we're small. Yes, we're temporary, but we're also remarkable. The fact that matter can organize itself into forms capable of thought, capable of science, capable of understanding the universe is extraordinary. The universe is vast and mostly empty, but here and now, in this tiny corner, something amazing has happened. Atoms that were forged in stars have come together in arrangements that can contemplate those stars. You are a way for the universe to know itself. This isn't poetry or metaphor, it's literally true. The atoms in your body were created in stellar interiors billions of years ago. They've been part of clouds and rocks, and perhaps other living things before finding their current configuration as you. And now, through you, the universe has developed the ability to study its own history, to look back in time and understand how everything came to be. This perspective transforms insignificance into wonder. Yes, you're small compared to galaxies, but you're also unimaginably complex compared to a galaxy. A galaxy is mostly empty space with stars following simple orbital mechanics. You're a concentrated region of extraordinary complexity. Trillions of cells working in coordination, a brain with billions of neurons creating consciousness, thought, emotion, meaning. Scale isn't the only measure of importance. A galaxy is large but simple. A human is small but complex. Which matters more? The question doesn't have an objective answer, which perhaps is the point. Meaning and significance are qualities we assign, not inherent properties of physical systems. The observations of distant galaxies remind us of this. Those galaxies are real, physical objects governed by the same laws that govern us, but they don't care about themselves. They don't wonder, don't question, don't seek understanding. They simply exist, matter and energy interacting according to physics. Either way, whether common or rare, our existence matters because we say it matters. The universe doesn't judge. It doesn't assign value. But we do. And in that capacity to assign meaning, to create value from our choices and relationships and efforts, we transcend our physical insignificance. The distant universe, beautiful and vast and ancient, serves as both humbling reminder and inspiring context for human existence. We're small, yes. Temporary, yes. But also aware, understanding, capable of finding joy and creating meaning in the time we have. And that's not nothing. That might in fact be everything that matters. As we continue forward, let's explore how this cosmic perspective shapes our understanding of time, of the universe's history and future, and of our own moment within that vast chronology. The universe has a direction. Time flows from past to future, and things change in consistent ways. Hot objects cool, complex structures break down, ordered systems become disordered. This directionality is captured by the concept of entropy, a measure of disorder or randomness in a system. The second law of thermodynamics tells us that entropy always increases in closed systems. Disorder naturally grows, order naturally decays. This isn't just a tendency or preference. It's a fundamental law governing how physical systems evolve, and it applies not just to laboratory experiments but to the entire universe. The early universe had very low entropy. After the Big Bang, despite being extraordinarily hot and dense, the universe was remarkably uniform. Matter was distributed almost evenly, with only tiny variations from place to place. This uniformity represents a low entropy state, a high degree of order compared to what would come later. As the universe expanded and cooled, entropy increased. Matter clumped into structures. Galaxies formed, creating regions of high density separated by voids. Stars formed within galaxies, concentrating matter even further. Planets formed around stars, and on at least one planet, complex chemistry gave rise to life, creating extremely ordered structures like cells and organisms. Wait, the universe doesn't care which we choose. If entropy always increases, how can structures become more complex and ordered over time? How can the universe go from smooth uniformity to rich structure and diversity? The universe doesn't care which we choose. It continues on its thermodynamic path regardless of our feelings about it. But we care. And our caring, our capacity to assign meaning and value, transforms the cold physics of entropy into something richer. Observations of the distant universe give context to our existence. They show us where we came from, how the structures that led to us formed and evolved. They show us the universe's youth, letting us compare then to now and extrapolate toward the future. They're a cosmic mirror reflecting our origins and our likely fate. But they also show us that the universe is dynamic, not static. It changes, evolves, creates new structures even as old ones decay. We're part of that ongoing process, products of cosmic evolution, and perhaps agents of future change. What we do with our brief moment of awareness, how we shape the world around us, contributes in some small way to the universe's story. And that leads us to consider one final aspect of our relationship with the cosmos, the question of whether our observations and understanding have any effect on the universe itself, and what it means to be observers in a quantum cosmos. In quantum mechanics, observation isn't passive. The act of measuring a quantum system affects that system, collapsing its wave function from a state of multiple possibilities into a single actuality. This is one of the strangest features of quantum theory, and it's led to endless philosophical debates about the role of observers in physical reality. But it's undeniable that we are observers, that we exist and can study the universe. And our observations do matter, at least to us. Every measurement we make, every galaxy we catalogue, every spectrum we analyse, contributes to our understanding. We're mapping the cosmos, building a picture of its structure and history that didn't exist before conscious beings started asking questions. In that sense, observers do affect the universe, not physically but informatively. We create knowledge, understanding, meaning. Before life emerged on Earth, the universe existed but was unknown, uncontemplated, unstudied. Now, at least in this tiny corner, the universe has developed the capacity to study itself through us. This self-knowledge of the universe through conscious observers is remarkable. Think about what's happening when you look at an image from Webb showing distant galaxies. Light travelled billions of years from those galaxies. That light entered the telescope, was detected by sensitive instruments, converted into electronic data, transmitted to Earth, processed by computers, turned into an image. Then that image entered your eye, was converted into neural signals, processed by your brain, and became conscious experience. You're aware of seeing distant galaxies. You can think about what they mean, how they formed, what they tell us about cosmic history. The universe has, through this chain of physical processes, achieved self-awareness, at least partially and temporarily. That's not metaphysics or mysticism. It's a straightforward description of what's happening. Matter organised into particular forms, biological and technological, has enabled the universe to observe and understand itself. And this self-observation, this self-understanding, is something genuinely new in cosmic history, at least in our corner of space. This asymmetry between observer and observed, between the knowing and the unknowing, is fundamental to our relationship with the cosmos. We're aware of the universe on scales from subatomic particles to the cosmic horizon. The universe, for the most part, is unaware of us. We exist within it, made of its matter, following its laws, but adding to it this strange quality of awareness and understanding. And as we move into our final act, let's consider what all these observations and realizations mean for how we think about our existence, our future, and the cosmic journey we're all part of, whether we recognize it or not. We've journeyed far together, across billions of light years and billions of years of cosmic history. We've seen surprising galaxies, unexpected structures, mysterious dark components that dominate reality. We've contemplated our place in this vast cosmos, the meaning we create from cosmic insignificance, the way observers relate to the universe they observe. But for all we've discovered, for all the knowledge we've accumulated through decades of astronomical observation and theoretical development, vast territories of ignorance remain. There are fundamental questions we simply can't answer yet, mysteries that persist despite our best efforts. What is dark matter? We've measured its effect countless times, mapped its distribution across the cosmos, determined that it makes up most of the matter in the universe, but we don't know what it's made of. Decades of experiments searching for dark matter particles have found nothing definitive. The substance dominating the universe's mass remains invisible and unidentified. What is dark energy? This is even more mysterious than dark matter. We know the universe's expansion is accelerating. We've measured this acceleration multiple ways, but we have no compelling explanation for what causes it. Is it Einstein's cosmological constant? Is it a field that can vary? Is it a sign our theory of gravity needs revision? We don't know. Why did the universe begin in such a low entropy state? The Big Bang represents an extraordinarily ordered initial condition, with matter distributed almost uniformly. Why? What set those initial conditions? We can describe what happened after the Big Bang with impressive precision, but we can't explain why the universe started the way it did. What happened before the Big Bang? This might not even be a meaningful question. Time itself might have begun at the Big Bang, making before a nonsensical concept. Or perhaps the Big Bang was just a transition in an eternally existing cosmos. Or perhaps there are multiple universes, each with their own Big Bangs. These ideas remain speculative. Why do the fundamental constants have the values they do? The strength of gravity, the electromagnetic force, the mass of elementary particles, all these seem arbitrary. Change them slightly, and the universe would be radically different, likely unable to produce complexity or life. Is there a deeper theory that explains these values, or are we just lucky to exist in a universe with suitable constants? These are not small questions. They touch on fundamental aspects of reality, on the deepest levels of physical law and cosmic history. An honest assessment requires acknowledging we don't have answers. We have speculations, hypotheses, theoretical frameworks, but we don't have confirmed, tested, widely accepted answers to these deep mysteries. Science is comfortable with this ignorance in a way that might seem strange. We don't pretend to know things we don't. We don't invent answers just to fill gaps. We say quote 3 and keep working, keep observing, keep testing ideas. This humility, this willingness to admit ignorance, is one of science's great strengths. And it means there's always more to discover, Always new frontiers to explore. Each answered question reveals new questions. Each mystery solved exposes deeper mysteries. The process never ends, because nature is rich and complex and deep beyond our current understanding. This knowledge didn't come easily. It represents centuries of work by thousands of people, countless observations, endless calculations and debates and refinements. But we have it now, a coherent picture of cosmic evolution that connects the beginning to the present and extrapolates toward the future. And as we continue this final portion of our journey together, let's contemplate what this knowledge means for how we think about ourselves, about our civilization's place in cosmic history, and about the responsibilities that come with awareness and understanding. Here's something worth sitting with for a moment. Of all the matter in the universe, only an infinitesimal fraction has organized itself into forms capable of awareness. Most matter is in stars or diffuse gas or locked up in planets and asteroids. It exists, it follows physics, but it doesn't know it exists. Then there's us, and perhaps others elsewhere, though we haven't confirmed their existence yet. Matter that knows it exists. Matter that can contemplate the universe, ask questions, seek understanding. This is extraordinary, a cosmic fluke of staggering improbability. This doesn't mean we have to do anything grand or cosmic. Most of meaning and value operates on human scales, relationships with others, personal growth, creative expression, helping and being helped. These aren't cosmically significant, but they're significant to us, and that's what matters. But we also have opportunities for something broader. We can contribute to collective human understanding. We can build on the knowledge previous generations accumulated. We can push the boundaries of what's known, whether through scientific research, artistic creation, technological innovation, or simply thoughtful engagement with the world. And we can contemplate our place in the cosmos, as we're doing now. This contemplation doesn't change the universe. Distant galaxies continue their evolution whether we think about them or not. But it changes us. It provides perspective, context for our existence. It reminds us that we're part of something vastly larger than ourselves, while also being unique and valuable in our awareness. Looking at the edge of the universe, at light from galaxies billions of years old, we're exercising this privilege of awareness. We're taking the cosmos's gift of consciousness and using it to understand cosmic history. We're connecting our brief individual existences to the grand sweep of universal evolution. And there's something profound in this act of connection. We're temporary, yes, but we're connected to permanence through our material composition. We're small, yes, but we're connected to vastness through our place in cosmic history. We're insignificant by many measures, yes, but we're connected to significance through our capacity to create meaning. This privilege of awareness comes with no external obligations. The universe doesn't require us to do anything with it. We could ignore cosmic questions entirely, focus only on immediate concerns, and nothing cosmically important would change. But we have the option to engage with these larger questions, to use our awareness to explore and understand. Future generations might have even better instruments and deeper understanding. But they'll build on what we know now, just as we built on what previous generations established. The knowledge accumulates, generation by generation, observer by observer, question by question. And all of this happens because matter became aware, because the universe, through its evolution, produced forms capable of studying themselves in their context, because we exist and choose to engage with cosmic questions rather than ignore them. It's easy to take this for granted. It's easy to forget how remarkable and improbable and precious this awareness is, but occasionally, perhaps when looking at an image of distant galaxies or contemplating the universe's history, the remarkability breaks through. We remember, briefly, what an extraordinary privilege it is to be aware, to understand, to connect our existence to cosmic reality. And with that thought settling gently in your mind, let's explore how this cosmic awareness connects to questions about our future, and the choices we make with our brief moment of consciousness. When we look at the edge of the universe, we're looking into the past. Ego have continued evolving. By now, ego have continued evolving. By now, they're unrecognizable from what we observe. Stars have lived and died. Black holes have grown. Galaxies have merged. The universe, those distant regions, represent no longer exists. But it once did. And it reminds us that the universe we inhabit now is equally temporary. The galaxies we see around us, the stars in our night sky, even our own Milky Way, all will change beyond recognition given enough time. Nothing stays the same. Everything evolves according to physics, following trajectories we can partly predict, but never fully control. There's also the question of whether we're alone. We've found no evidence yet of other intelligent life. No signals, no artifacts, no unmistakable signs in our observations of exoplanets or distant galaxies. But absence of evidence isn't evidence of absence, particularly when we've only begun searching systematically. The universe might be teeming with life and even intelligence, or we might be extraordinarily rare, perhaps the only technological civilization in the observable universe. We don't know. And until we find compelling evidence one way or another, we should probably prepare for both possibilities. If we're alone, that makes us cosmically precious, the only known instance of matter becoming conscious and asking questions about itself. It also makes our survival crucial in a way it wouldn't be if intelligence were common. We'd be responsible for preserving this cosmic fluke, this remarkable development in universal evolution. If we're not alone, that changes everything about our self-conception and our future. Contact with other intelligence would be the most profound development in human history, fundamentally altering how we think about ourselves and our place in the cosmos. And if other civilizations exist, some might be far older than us, having had billions of years to develop. What would we learn from them? What would they have discovered about cosmic reality that we haven't? These are questions without current answers, but they're worth contemplating as we think about humanity's potential futures. Every choice we make now affects which futures remain possible. Every generation passes on a world to the next. Hopefully improved, but at minimum sustained. The universe has given us the gift of existence in a region and time when consciousness is possible. It's assembled matter into forms capable of appreciation and understanding. What we do with this gift is up to us. There's no cosmic authority mandating particular choices. We're free to squander the opportunity or make the most of it. And perhaps that's the ultimate message from observing the edge of the universe. The cosmos is vast and old and largely indifferent, but here and now we exist, aware and capable. We can observe and understand and create meaning from our brief moment of consciousness. That's not nothing. That might in fact be everything that truly matters. Let your breathing slow as we prepare for our journey's end. Feel the weight of your body, the surface supporting you. We've travelled far together, across billions of years and light years, contemplating mysteries and certainties alike. And now we begin our gentle descent toward rest, toward the peace that comes from understanding and acceptance. We've journeyed to the edge of everything observable, seen light that travelled for billions of years, contemplated galaxies as they were when the universe was young. We've wrestled with mysteries, acknowledged ignorance, celebrated understanding. And through it all, a pattern has emerged, a theme worth carrying with you as you drift towards sleep. The universe is incomprehensibly vast, ancient beyond easy understanding, full of phenomena that dwarf human concerns. And yet, within this vastness, we exist. We're made of atoms forged in stars, assembled through billions of years of cosmic evolution into forms capable of awareness. We can observe and understand, create meaning and find beauty, connect our temporary individual existences to the eternal cosmic story. So as you prepare to sleep, as your consciousness dims and you drift into dreams or into dreamless rest, carry this thought with you. You're part of the universe experiencing itself. We'll continue their evolution. The cosmos will continue their evolution. The cosmos will expand and cool. Stars will be born and die. And none of it requires your awareness or concern. You're free to rest, to let go, to simply exist without the burden of cosmic significance. Understanding and appreciating the understanding and appreciating the universe you're part of. You can look at images of distant galaxies and comprehend what you're seeing. You can contemplate cosmic history and your place in it. You can find wonder and beauty in the fact of existence itself. This is enough. This is more than enough. The universe has given you consciousness, and you can use it however you choose. And right now, in this moment, you can choose to rest, to let your awareness dim, to trust that the cosmos will continue its evolution without requiring your participation. The edge of the universe, that distant realm we've explored together, it's still there. Billions of light years away, ancient light still travelling through space. And it will be there tomorrow and the next day and for billions of years to come, waiting patiently for observers to find it, to wonder at it, to incorporate it into their understanding of reality. But tonight you don't need to be that observer. Tonight you can rest in the knowledge that the universe is vast and beautiful and full of wonders, and you had this moment to contemplate some of them. Tomorrow brings other opportunities, other moments of awareness. Tonight is for letting go, for trusting in the cosmic processes that have sustained you thus far, for allowing consciousness to dim and rest. Let the vastness of space and time hold you gently. You're part of it, made of it. Returning to the unconscious peace that most matter enjoys. Sleep well, knowing that the universe continues its patient evolution, that consciousness will return with morning light, that existence is both miraculous and ordinary, both profound and simple. The journey ends where it began, with you, here and now, breath slowing, thoughts quieting, body heavy and warm, drifting gently toward the rest that all conscious beings need. The edge of the universe has shown us wonders. Now it's time to close our eyes and let the wonders fade into peaceful darkness. Thank you for staying with me on this long journey to the edge of everything. We've travelled together across billions of light years and billions of years, from the most distant reaches of space and time back to this quiet moment, here and now, wherever you are in the world. From the first surprising galaxies that formed too quickly to the black holes that grew impossibly fast, from the mysteries of dark matter and dark energy to the meaning we create from cosmic insignificance, we've explored the universe's deepest questions and most distant realms. We've seen how observations challenge understanding, how each answer spawns new questions, how the cosmos remains endlessly fascinating despite our best efforts to comprehend it completely. And through it all, one truth has emerged as clearly as ancient light from distant galaxies. We're part of this cosmic story, products of billions of years of evolution, temporary but aware, small but conscious, capable of understanding the universe that created us. That's not something to take lightly, that's something profound, something worth acknowledging as you prepare for sleep. The answer to what scientists found at the edge of the universe that might seem disturbing is this. They found a cosmos that doesn't match our expectations perfectly. Galaxies and structures that formed faster than... Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed, and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. Galaxies and structures that formed faster than predicted, black holes that grew more quickly than models suggested, a universe more dynamic and active in its youth than we imagined. But perhaps what's truly unsettling isn't the observations themselves, but what they reveal about the limits of our understanding. The vast territories of ignorance that remain despite our sophisticated instruments and elegant theories. Yet maybe that's not disturbing at all. Maybe it's exactly as it should be. The universe doesn't owe us simple explanations. It's under no obligation to match our expectations or conform to our theories. It simply is, following its own laws, evolving according to physics we're still working to fully understand. And we get to observe, to wonder, to gradually build understanding through patient effort across generations. If you enjoyed this slow drift through cosmic mysteries and deep questions, if these quiet explorations help you find peace at day's end, a like and subscribe would be wonderful. It helps others discover these journeys into the unknown. And to those already subscribed, thank you. Your presence here makes this shared exploration possible, makes these long contemplative journeys worth creating. I'm grateful for your time and attention, for your willingness to wonder alongside me about the deepest questions we can ask. Wherever you are in the world right now, in whatever space you've claimed for rest, I hope you're comfortable. I hope your breathing has slowed into the gentle rhythm that precedes sleep. I hope the weight of cosmic vastness has settled into something like peace, a perspective that makes your concerns feel appropriately scaled, while making existence itself feel precious and strange. I hope your thoughts have quieted, or at least softened, the urgency of daily life replaced by the timeless patience of cosmic evolution. I hope your body feels heavy and warm, held safely by gravity, by the surface beneath you, by the same forces that hold galaxies together across billions of light years. Look up if you can, at the night sky, or imagine it if you can't. All those points of light, those distant suns, they're out there right now, burning their fuel, creating elements, following the same physics that governs everything from the smallest particle to the larger structure. And somewhere among those stars, light is beginning its journey that will arrive billions of years from now at some distant observer, carrying information about this moment in cosmic history. You're part of that history. Your atoms were created in stellar furnaces. Your consciousness emerged from billions of years of evolution. You're standing, or lying, at a particular moment in cosmic time, a participant in the universe's ongoing story whether you recognize it or not. And in the end, what we've learned from observing the edge of the universe is both simple and profound. The cosmos is vast and ancient and strange, full of phenomena that challenge our understanding and mysteries that might never be fully resolved. But within this vastness, we exist. We observe and understand and create meaning. We transform unconscious matter into consciousness, blind physics into purpose and appreciation. That's enough. That's more than enough. The universe has given you existence, awareness, the capacity to contemplate these questions. What you do with that gift is up to you. But tonight, in this moment, you can simply rest in the knowledge that you're part of something vastly larger than yourself, while also being unique and valuable in your awareness. Sleep well, friend. Dream of galaxies if dreams come, or rest in dreamless peace if they don't. Dream of ancient light travelling billions of years to reach human eyes, of matter organising itself into ever more complex forms, of consciousness emerging from unconscious physics like a flower from soil. Dream of the edge of everything, that distant realm where light from the universe's youth still travels through space, where galaxies were just forming, where the cosmic story was still being written. And know that the story continues, that you're part of it, that your brief moment of awareness contributes to the universe's ongoing becoming. The mysteries remain, the questions persist. The edge of the universe holds its secrets still, even as we learn more with each new observation. But that's tomorrow's concern. Tonight is for rest, for release, for letting the cosmic vastness hold you gently as you drift into sleep. Good night. Sleep peacefully. Let the universe continue its patient evolution while you rest. And when morning comes, when consciousness returns and the day's concerns reassert themselves, remember this journey we've taken together. This contemplation of the deepest questions and most distant realms. Remember that you're part of the cosmos, connected to everything from the smallest particle to the largest structure, temporary but aware, small but conscious, able to find meaning and beauty in the brief opportunity existence has given you. Rest well. The stars will still be there tomorrow. The universe will continue its expansion, its cooling, its slow increase in entropy toward distant heat death. But that's billions of years away. Tonight you can simply be, exist, rest in the safety of this moment. Good night.